Hi everybody. So we are at module number 4 where we are studying how material fails. So we are basically studying structure, fatigue and creep phenomena for the area of materials. So last time, in the last video, we have studied two types of fracture mode, brittle and ductile fracture modes. Okay. Then we studied Griffith theory, right, to determine the critical stress for fracture for glass kind of material, brittle material, and also for the metals. That is called as Horowitz modification. Now we will see ductile to brittle transition temperature for different metals. Right? So as we know, properties, mechanical properties, they are changing with the time. For instance, we could easily realize that steel becomes ductile, that is flexible, above 0 degrees Celsius and becomes brittle, like breaks like glass below 0 degrees Celsius. So, to find out uh, the impact resistance of material, this is strength in that sense, a notch bar impact test is usually carried out. Okay, and we come to know ductile to brittle transition at different temperature. Right, so this impact test is carried out at a different temperature, and at what temperature it fails, that can be understood. Okay, so this is what the plot for these ductile to brittle transition phenomena for steel. Okay. So here uh, we have impact value, okay, at x-axis, at y-axis we have variation temperature, increase in temperature. Okay. So so basically we have a object of a steel, or you can say sample of steel, and that is subjected to impact value at different temperatures. Okay. So we have three zones. So at low temperature, right? So especially below 100 degrees Celsius, we have brittle zone. So steel becomes brittle and breaks like glass below minus 100 degrees Celsius. But above this minus 100 degrees Celsius, then 0 and up to say approximately 120 degrees Celsius, okay, we have transition from this brittleness or brittle nature of steel into ductile nature. Ductile means flexibility, right? There is a plastic deformation, okay, movement of dislocation on application of stress during impact test. Okay. So above minus 100 degrees Celsius and up to approximately 120 degrees Celsius, there is a transformation, okay, in impact value. So brittleness is progressively reduced as temperature is increased, okay, and above 120 degrees Celsius, it becomes a complete ductile. Okay. So this plot shows us the nature or fact, nature of the mode of failure for steel. So below minus 100 degrees Celsius, steel will break like glass. And between minus 100 degrees Celsius and up to 120 degrees Celsius, there is a transformation from brittle to ductile progressively. And above 120 degrees Celsius, it is completely ductile. So this ductile to brittle transition is exhibited by BCC metals, body centered cubic metals like low carbon steel, right, which is usually brittle at low temperature. So with FCC, this is not the case. FCC, they remain ductile even at low temperature. Okay. So in metal, plastic deformation at room temperature occurs by dislocation motion. We have already studied this. It's plastic deformation, which is actually responsible for ductility of metals. Okay, it is accompanied by the dislocation. Dislocation starts moving when we apply stress. Okay, and that is at room temperature. So if stress required for moving dislocation is high, then metal will fail by brittle. So basically, if the stress for movement of this location, which is responsible for the plasticity or ductility, if the test stress required is high, then metal will fail without plastic deformation. So no ductility. So it will fail in a brittle way. And if dislocation motion is facilitated, then ductile fracture. So for ductility, dislocation motion should be feasible. Then only there is fracture. So the mode of fracture, ductile or brittle, changes at some temperature or temperature range, and that temperature range is actually called as a ductile to brittle transition temperature or range. Okay, so in FCC, so we have studied austenite phase, FCC, phase centered grip. Okay. The force required for dislocation motion, okay, when we apply stress, so we need to have dislocation motion, okay, to have a ductility or flexibility. So force required for dislocation motion is not temperature dependent in case of abscissing, and hence it is ductile. Okay. So this is what the subplot for different types of skills which are different in percentage of carbon. Okay. So here we have the plot for iron. You could see this zone is called the transformation zone. It will be ductile transformation. And above this, from this, we have complete this, ductility. Okay. And below this, there is a brittle failure. Okay. So it is changed with nature of the plot changed with change in percentage of carbon. From 0.45% carbon steel, failure will occur in this transformation steel. For 0.6% carbon steel, transformation is different. So with the help of these plots, we can determine the operating range of a material. Okay, so at what temperature material becomes brittle and breaks glass, and at what temperature then it is safe. So we can determine. So these are the practical examples happened in the past. So you must have known about this. Right? So disastrous incidences with the Titanic, with the Titanic liberty ships. So they were happening due to the calculated transition and of steel. So at low temperature, ductility was completely reduced and ships break right. Then next is fatigue failure. So fatigue, when we talk about fatigue, we must understand that the article is under cyclic and compressive and tensile load. So moving shaft, or if we bend any rod, so that is means by moving up and down. Okay, so that is example of a fatigue stress, and the rod will fail at particular cycle. So is the formation and propagation of cracks due to repeatedly. So, so most fatigue failures are caused by cyclic load significantly below the load that between yielding of it. Means under cyclic loading, means compressive and tensile stress, material will fail below even ultimate tensile stress. Means at yielding stress, it will break. Okay, actually it is supposed to break at ultimate tensile stress. But due to cyclic loading, repeatedly or cyclic loading, material fails even at yielding or aid strength. So the failure occurs due to cyclic nature of load, which is macroscopic progress imperfections to flow into macroscopic. So this is what actually mechanism. How material fails in the fatigue finale. Okay, so there is a formation of microscopic cracks. Initiation phase. So my any component or any process happening always has imperfectly flux. So under cyclic loading, crack starts initiation. That is called as the initiation of the macroscopic, the visible. The crack then propagates to critical size. That results in fracture that we are showing in. So once due to flaws in the circuit loading, microscopic cracks penetrating and those cracks are propagated into the temple. So this is what example I told you just now. There is a thin rod steel that bending with back and forth series. You can try this. Okay, you can bend steel rod back and forth. So the part which is bending, inside part is bending, is under compressive stress, and outside part is under tensile stress. And that rod will fail, okay, at particular. So there are three types of cyclic stresses also. So first is reverse stress cycle. So this A is an example of reverse stress cycle. The stress alternates from maximum tensile stress to positive stress to minimum compressive stress, okay, of equal magnitude. This is important. Magnitude is same. Okay. So just I just told you the example of the bending of a rod. Okay. So you can have a tensile stress, positive stress, and minimum compressive negative stress. Then second example is repeated stress cycle. So here maximum and minimum stress levels are not equal. So asymmetrical kind of failure, okay, or stress. This is you could see. Here we have a positive value of the stress and negative value of the stress. Here it is not the case. And third is a random cycle. Okay. So, random stress cycles. Okay. So this random stress cycle, so this is actually complicated stress, and it is observed mostly in case of aircraft wings, okay, which are subjected to the unpredictable overloads or strong winds, okay, and that leads to fatigue. So this is what the random stress cycle. Okay. Then in sigma r is range of stress in all three cases. So sigma maximum minus sigma minimum will be the range of stress. Then amplitude of stress sigma a will be sigma r, the range of stress divided by 2. So range of stress is sigma x minus sigma maximum minus sigma minimum and divided by 2. We can have amplitude of the stress. Then mean stress also can be determined by this formula. Maximum stress plus minimum stress divided by. Then mechanism of fatigue failure. How fatigue actually fails in the cyclic loop. This fatigue. So in this case, fatigue fracture always starts as a small crack which under repeated loading of stress grows in size. As I told you before, any component process component has flaws. And under cyclic loading, there is an initiation of a crack. Okay? And that the crack is then propagated. It divides and galvanized. So that is shown in this figure. So first step is crack nucleation. Okay? At flaw, any flaw in component under cyclic loading, there is nucleation of a small crack. Okay? Let's crack nucleation. fatigue failure begins with obviously small crack, generally on the surface. So in the first stage. Then once crack is initiated or nucleated, it starts propagating in the direction perpendicular to the direction of the tensile axis. So tensile loading is applied in this direction, up and down. The crack started propagating in this direction. It is perpendicular to the axis of tensile loading direction. Then third step, fracture. So these are the two steps how crack propagates, shown in the crack growth step. And the third step is the fracture. Okay? So fatigue crack front thus advances during each stress cycle, which is shown as minor ripple. So this ripple lines is the progress of growth of a crack. Okay? So and material effects. These are the three steps. So these ripple lines originated from crack are visible only from very high powered microscope. So we can observe this under microscope. Okay, under microscope. How crack with tracks actually. It shows tracks with ripple lines, which shows ripple lines shows the progress of a crack. Overall mechanism involves propagation of crack slowly from the surface, and the fracture surface rub together due to pulsating nature of stress and becomes hard, what is shown in the figure, the last. So fatigue cracks are not the result of brittle fracture but of plastics. This is a very important statement. Fatigue crack is not a brittle failure, right? So plastic deformation is there. So you must know this. So it is because of plastic slip at a particular level. We have studied already this slipping, critical resolve stress and all. We already done. So there are three steps: initiation, then growth, and failure. Fracture. So this is what the experimental setup for fatigue testing. This is called a roller fatigue testing machine. So the specimen is in the form of cantilever and loaded at the end. It is shown here. Okay. So this is what the instrument. We have two setups, one from this side and another from this side, and we have a machine to rotate the specimen. Okay. And here loading is being done. Okay, for this specimen over here and for another specimen over here. So basically we have cantilever which can be loaded at the end and fixed at the another end. So this is specimen is fixed at this end and loaded at another end. Okay. It is rotated, the specimen is rotated by means of high speed motor and number of rotations are made. So it is then rotated under load, known load, and rotations are measured. The specimen is thus subjected to cyclic stresses and number of cycles to failure are counted. Okay. So at which cycle, which rotation it fails, that can be determined. So at any instant, the upper surface of specimen is under tension and lower that we can easily realize because stress or load is applied in this direction downward. So when it starts moving, upper portion is undergoing bending, right, and also moving, rotating. So the upper part is under tensile stress and lower part is under compressive stress. So this is one rotation. Sorry, thus in was one rotation, Sisyphon undergoes two cyclic fluctuations of tensile and then compression. Again tensile, compression. So okay, it is continuing till material fails. So number of rotations they are counted. Okay, and stress also known for further calculation. The number of cycles to cause failure will vary with applied stress. So it is stress dependent. Okay, how much load we are applying. Okay, so that decides number of cycles for failure. If obviously stress is high, means load is high, number of cycles will be low. Very high. Here the stress, sorry, higher the stress, lower will be the cycles to our. That is what I just told you. stress if stresses have over the surface uh, because the data available stress value and number of the data that is plotted. The data then plotted as stress versus log of number of age of cycles. That is called as the SN curves. So there are two distinct types of SN curves or SN behaviors observed in different metals. So first we see ferrous alloys, iron-based alloys is stable, which is a major engineering material, and then we see non-ferrous alloys. So this is called as a typical SN curve for iron-based alloy or steel. So this is plot of stress applied versus number of cycles to failure. So if you observe this plot, so initially stress is high, okay, it's high at peak value. So material fails with less number of cycles, with less earlier. So as stress is reduced, number of cycles to failure obviously keep on increasing. Okay, up to the particular value of the stress. That is called the fatigue limit or endurance. Okay. So, sorry, fatigue limit. So here, mm, at about this, if you keep on increasing stress, right? So the number of cycles will be also increasing, and material will not fail. Material will be served for more number of cycles. Okay, so it is so at particular value of the stress. Okay, so what happens is shown in this plot. So for some iron-based and titanium alloys, the SL curve becomes horizontal at higher N values. So here it has become horizontal, higher N values, higher N. The stress level below which fatigue failure will not occur. Okay, fatigue failure will not occur. It's called fatigue limit or endurance. Okay, so actually endurance in the fatigue limit is what? It is stress value below which fatigue failure will not occur. Another failure or another kind of failure may occur. Not exactly failure, theory failure will not be occur. Okay. Now for non-ferrous or aluminum or magnesium based alloys, we have this type of plot, right? So here for non-ferrous metals like aluminum, magnesium, copper, and their alloys, no such stress limit exists. Okay? So as the stress is decreased, number of cycles to failure is increased. Okay, but there is no or that plot or SN curve is not horizontal. Okay, and okay, if this when number of cycles keep on increasing, with decrease in stress. So for these materials, the fatigue response is specified as fatigue strength. How to specify fatigue strength for such material? Okay, because there is no specific value as we observed in ferrous alloy. There is a specific value. So below that stress, but there is no fatigue value, irrespective of the number of cycles. But in this case, as stress is decreased, the number of cycles are increased. So in this case, fatigue strength or endurance limit is defined as the stress level at which failure will occur. It's shown over here. So at particular stress, that material will survive so and so. Understand? So this is a way to express fatigue strength for this non-ferrous material. So endurance and fatigue strength is the maximum stress that can be applied repeatedly over a specified number of cycles without okay. So endurance limit of fatigue strength in this case is what? The maximum stress that can be applied repeatedly in circuit loading over specified number of cycles without failure. So here, in this case, this material, endurance limit will be this stress. Okay. Then factors influencing fatigue. First is notch. Having notch. Crack. You know, fatigue strength is reduced by presence of notch in the notch. Okay, so during processing of component, cracks are always okay, so that affects the fatigue level. Okay, endurance level. Fatigue strength. The fatigue effect is studied with specimen containing V notch. We purposely create a V notch in the specimen and its fatigue phenomena is specific. The effect of notches on fatigue strength is determined by comparing the SN curves of notched and unnotched specimen. So same specimen with notching, okay, what is the fatigue strength, and with unnotched state, what is the fatigue strength that can be compared, and then fatigue strength is determined. Then corrosion is fatigue. So this is again one type of severe type of failure of material. Okay. So corrosion we have already studied. Okay. So this is electrochemical attack of environment on metals. So the simultaneous action of cyclic stress and electrochemical attack of environment is called corrosion of electrochemical attack and fatigue is cyclic stress. Combined effect. So severe, severe case of corrosion leads to pitting. You know that. Corrosion leads to pitting, formation of pin. In so these pits act as notches and various fatigue theoretical strength cannot be achieved because corrosion, corrosion phenomenon, there are pits or pinholes and the pits act as notches and they those notches reduce fatigue strength. Crack propagation and consequent failure is always accelerated when corrosion and fatigue occurs. So, I told you, this is the failure case of failure of crack propagation and then failure. It accelerates. Okay, the electrical attack is corrosion and fatigue is cyclic. Corrosion fatigue test is carried out by subjecting specimen in combined influence of corrosion environment with cyclic stress and the value. So meaning of this is so this is kind of simulation, okay, done in laboratory. Okay. So in corrosive environment can be created in laboratory and object test is carried out. Okay, so we can determine corrosion fatigue strength. The metals are protected from corrosion fatigue by applying metallic and non-metallic coatings. So, that is especially to avoid the contact of the specimen with the environment coating the corrosion fatigue can be minimized by nitriding process. So, this is one more surface treatment in the steel. Thermal fatigue is the third factor influencing. Thermal fatigue is produced due to fluctuating thermal stresses and not mechanical stresses. Okay? So in the previous cases we observed mechanical stresses. We applied load, but here due to thermal shocks, thermal stresses, and to the fluctuating, okay? Thermal fatigue is observed. Thermal stress developed in specimen by temperature change delta T, okay? And that is given by sigma thermal stress that is developed, okay, due to changing temperature is equal to alpha into E into delta. So alpha is coefficient of thermal expansion, the property of material. E is elastic modules, and with the help of these two values and temperature change, we can explain the thermal stress. So austenite steel is sensitive to thermal fatigue due to its low thermal permeability and high specific. Okay. So thank you. So we will stop here.